Hey guys, welcome back to image processing tutorial. This is episode number 1. Last episode we had the intro. In that intro we saw why we need image processing. We saw about KFC chicken and when a lot of chicken come, how KFC manages that, and that's going to be a problem for us. Then we invented the image processing. With image processing we can do a lot of massive things, very amazing things we can do with that. So that's what we saw in last episode, why we need image processing. Hi Lena. So I was joking. So in this episode we're gonna see the basic definition of an image. And about image, what is an image? Yeah, this is an image. Yeah, you guys can see. So basically image is an 2D representation of the word to go. Yeah, that's it. 2D representation of the 3D world. So 3D world, basically 3D is the basic world we have here. This is the scenery. In the scenery, in this 3D scenery is the, so we are remembering that 3D scenery. We can recreate the 3D things because we can recreate 3D things, but yeah, you guys know what I really meant there. You can create this space, this 3D scene. You can really create that. Yeah, you can really create. You can never do that. Okay, maybe technology advanced, you can, but no, it's not possible. So in that case, but we want to see those things once more. We want to enjoy those things. So what we do, we just get our camera, get a picture like that. We store that 3D experience as a 2D world. That is what image is. So how does this, and about this image, a lot of things are there, like what we can see can be picturized. That is what we are seeing here. And the visible spectrum, that's what we things in the spectrum, the lights area, lights portion of the light that we can see. About the visible spectrum, it is around 400 to 700 nanometers, but there are some people who can see from 380 to 780 nanometers. Yeah, that's possible, but that's not common, man. Like X-Men guys, very powerful guys. So and then what about the other portion of light? Why can't we use it? Yeah, that's a question. And some scientists told, yeah, we can use it, like, because for the extraterrestrial those things, for the space exploration, space imaging, those in that area there are a lot of things that we can see. X-rays, yeah, we use X-rays for imaging for the medical purposes. We use infrared for the space imaging, those things, and a lot of other portions of light is also used in the imaging techniques. But we are not just aware. Maybe X-rays we might be aware because we are using it for medical reasons. Other things we are not aware because we don't go for space things. Yeah, we are not scientists. Maybe that. But for your knowledge, it is also used. And how is this an image? How is this image looking like? Like we can divide this image into different parts. Like we can divide the image into a Cartesian coordinate and those things. Okay, we wanna be dealing with that after some time. And suppose how is this image captured? And that's what we want to see. Like, yeah, camera, we use camera for getting the image, and that's a nice area. But what's working inside this camera? Camera has a sensor, yeah, sensor, a single imaging sensor. Like this sensor has got and how does this sensor look like? This is, so we can just say how this is working. Suppose this is a lens and this is the sensor there. And what we do is the camera sends some lights, as you seen camera as a flashlight, like that thing. And the like, it is not looking at what it sends, it's looking at what it's receiving. So it's a light from some source goes to an object, here it is A, and reflects to the camera's lens. Then it records the missing part of the light. That means which is the light, the portion of the light which is absorbed by the object, and with that it calculates the what was the color of that object, like that. Those we That's what basically the for camera techniques working. So an object absorbs some part of the light and it sends back in the other part. So the portion, like when the reflected light comes to camera, it stores that remaining part of the light that object sent to corresponding a position. Like that, it when the all light slide from all reflects from all part of the image in the portion, lens records all those reflected light in a square piece or piece like that. And basically that is what we call it as image. And in old cameras, what they do is, not in all cameras, in camera basically what we get is the reflected light misses some components of it, some portion of it, and we say that's a portion, that's the color of the real object. And what we do is we take the reverse, means we just subtract all those color, remaining color, that reflected portion of the light from the zero light. We say zero light, like the white light from light, we just subtract those things, then we get the missing portion, and that's the missing portion is the color of that. Like that we get the image. So basically a lot of stuffs are there, like and some we say when the light comes from that portion, means the reflected light comes, because it sometimes collides with the air particles like dust, and during those things, and during cold season we get blurred image, some not vague images we get. It's basically because of that, due to the water particles in the atmosphere, the again the reflected light get corrupted, means the original light get corrupted by colliding with the water particles. Those things happen and our image get vague. So basically those this much things are involved in imaging. And and about imaging, one form, few more things are there. And how does the image look like? Like yeah, yeah, this is what image look like. Image has got an, we can divide image into different small boxes, like horizontally uh, we divide image to maybe 500 boxes, and vertically we just divide it to 4. This is not actual size that we see here. And we this 500 and 400, that's around to 200,000, yeah, 200,000 boxes are there. Yeah, thousands, one, two, yeah, that's it. Yeah. So 200,000 boxes. So what is this 200,000 boxes? We can call it a name called pixels. So each pixel corresponds to one small rectangle. I can just zoom in here. Yeah, this is the smallest rectangle that we see here. You can see smallest rectangle, and each rectangle holds a value, like a small value, a mathematical value, some from maybe from 0 to 16 or 0 to 15, that's the range. 0 to 255, sometimes it might more. Uh, it holds a value, and that is what basically an image is. And corresponding to that value, we project. So if suppose the value that's in a pixel is maybe 255, and we corresponds that 255 to white color, and we corresponds the 0 to black color. And maybe if suppose if the one of the pixel had this height 125 as the value, we suppose this is the color of that 120 is a grayish thing, not actual gray but light type of gray. We say this is that 125th value of the pixel corresponding to. So like that each pixel has got some values, and for each value we give you some color. And like that, when we overall when we look at that that Cartesian coordinate, that box, that 500 into 400 box pixel value, that boxes, that total box collection with each box and value color corresponding to the value it's holding, we get the image. Yeah, that's basically image. We can just, we would like so maybe we can just get some examples. Maybe yeah, I don't know. This is in photo collection here. We just go home some yeah, pictures. Yeah, some cool pictures. Boom boom. Yeah, right. That's cool. So when we just zoom in here, you guys can see as we zoom in. Oh, sorry. Yeah, you guys Yeah, this is we are reaching a limit. Yeah, there comes a point when all, yeah, look at, we can see small portions of rectangles. When we, if we zoom in more, you can clearly, oh man, is there some, yeah, there's a command. Yes. Yeah, look at this. You see, you are seeing some weird boxes things. So these are basically pixels. If you put some grid like that, you can clearly see the that values. So basically, and pixel is like that. Pixel, each image is divided into pixels. Pixels holding some values, and we assign a color to the corresponding value, and that's what picture is. But there are few more things that we need to know, like. mm if you want to do some uh, when we have, like some values, so this pixel values, how much it can, what's the range of the pixel values, you guys might have seen somebody dealing with some 8-bit images, 16-bit images, those things. So what's this 16-bit, what's this 8-bit? We can say the pixel values. Suppose our pixel values, the value of a pixel can be from 0 to 255. 255 is 0 to 255 means around 256 values. Yeah, just right here, 0 to 255. Totally, there are 256 values. That means 2 raised to 8. Yeah, 2 raised to 8 values. So this we need 8 8 bits to represent this. So we need 8 bits. That is what the 8 bits those guys are referring to. It's about the pixel depth, how much variance, how much is this pixel from 8 bits. And some guys use even 16-bit images because those guys have good camera, more money, more bucks, they can make more images. And some guys more use 32-bit images. Usually we don't need those things, but for some purposes we need, for some big images, those things we need these things. So we need this 8 bits. But what's why are you using this 8 bits? We say there's a difference for an image from the scene, because we know, yeah, our scene, our world isn't continuous world, like but our digital continuous real world is turned into a discrete digital world in an image. And we can just say, like, suppose we are using a microscope. Yeah, my tongue hurts, that's fine. So with that microscope, when we are zooming in, and suppose we have a leaf, and when we are zooming into the leaf, we can see, as we zoom in, we will start seeing more small parts of the leaf. Like, initially it looked like some pattern guy, some kind of weird patterns, and then it grows to more. When we zoom in more, we gonna see the cells. Then when we zoom in more, we gonna see the nucleus. Okay, we are not gonna see because we don't have microscopes that visible like that. But there are powerful microscopes which can view those things, and we know that's how the nucleus and inner part of the nucleus, inner part, those things are being protons, those things, electrons, that have been discovered by those things. So we can see everything, each and every single minute detail in the real world. But in the digital world, that's not possible because our computers, our devices are limited. So they have to limit the values for something to some values. That's what we are doing in the discrete world. We are quantizing. We are limiting the values, quantizing the values. Suppose it was 16 point. 60.0000035, but a normal guy just want 16.0. That's it. That's what we are gonna quantize. And even in this digital, throughout course, we might not be using the decimal points. We might be using only 16. That's it. So that's what we are dealing about the quantization. So that's the difference from for the image from the scene. There is quantization. And about the brightness, that's what we want to say. Brightness is the value, because I told about the pixels, they are holding some values and we are giving some colors. So basically we are saying it is brightness of the, sorry, yeah, brightness of the that image. So this brightness, each pixel value having a pixel storing in value, and we call that value as brightness of that pixel. So 0 to 265, sorry, 0 to 55, that's it, yeah. 0 to 55 or some other 16-bit values, those things are corresponding to the brightness of the image. So basically we have the image is divided into pixels store the brightness. Yeah, that's what basically an image, that's all you want. So about the spatial sampling, we saw it, like yeah, this is what basically this is storing those things, that mapping those values to the from the real world to image. That's what spatial sampling is basically doing. And uh, now we're gonna see about the point spread function. So point spread function is basically we are arranging the, like we are drawing, we are using a function which corresponds to the brightness, the pixel values, yeah, brightness, and we are plotting it with the height. It's plotting its height which in which its height corresponding to the brightness of the image, the pixel value of the brightness of the pixel, that's the correct word. So like that we are, so basically that is what we are using, the point function. So point function is not continuous. Of course this is not continuous, because first value gonna be from the first pixel gonna be 0, then it's gonna be 1, then it's gonna be 2, like that goes in the horizontal or the vertical way. Not actually it should be 0, then 0.000001, then 0.000002, like that should go, but we are not doing it. Even that is a discrete case. Yeah, this is the point function that we do, but actually it's not the case. Actually this function is an continuous one, but what we use is a discrete one. So basically arranging this arranging according to the brightness value, its height, that's what we are doing in the point spread function. And that's the tutorial. And about last thing about the brightness quantization. So why do we need to quantize the brightness? Yeah, we say, why do we need to say only 8-bit? Why don't we use 16-bit images? Yeah, some photographers need the 16-bit images, but no, people just use 8-bit. Yeah, that's it. And even some guys use 32-bit images. Yeah, because they say they get a great scenery and they just captures it, and when they look into the picture they say, what a weird color this is. I captured something like light, dark, some kind of some portion big, brighter, like image scene, and what I got here just plain plain image. This is all dark. Yeah, so that's the problem. And photographers really care about the originality, means the coincidence of the scene and image. They really need it. And some there are more guys more are used, because some even in some imaging techniques we need those things. So we have to quantize the images. For normal people, for like Google Plus, they allow more size images in the actual size, but Facebook guys, they say, oh, we don't want those things, we just want to compress the image. You might lose the image quality, those things. No, I'm not comparing those guys, but I was just saying that, like that. So like how we want to quantize this image, we came to know about, like these guys don't want, some guys want 8-bit image, and some other guys for want 16-bit image for the same reason. And if a guy get the 816-bit image and he want to convert to 8-bit, how he gonna do that? Like he wanna sometimes, suppose he was 600 and he want to convert, and 600 was in the 16-bit case, so he just want to convert it. So what he gonna do? He gonna some like 600 divided by some 2 raised to 16. Yeah, that's the 16-bit image into 2 raised to 8. So he wanna do that like that. So why he wanna get the 16-bit image corresponding to the 8-bit image, he gonna downgrade it like that. And sometimes there are more problems like this. When we do like that, we might sometimes get suppose some in that case we got some suppose 2.0035. sorry this was, if we got a value like this, and we have to context this because we have, as I told, we have only 1 2 3 for those values. We don't have 1.2 2.2, so we have to context it. So we generate a rule like this, to point, if the value pixel value is greater than or equal to uh, x.5, then we say it as p equal to x plus 1, and else it's something like x. And that generally we use this rule, but sometimes this is not used for some medical purposes. We use something else, like we set the threshold as 2.1, like that we use. And sometimes even that threshold will be a variable, it might be changing according to the region of the image, those things. And a lot of things are like that. We don't want to deal with those things right now. We just want to say those things. This is not point 0.5. Basically 0.5 is not the generous, it's a standard, but we can generalize it for everything, because there are some reasons, some places where we need more things. So basically that's what I want to say today. I think that it was a bit lengthy, yeah, but doesn't matter. So this is what basically the image processing. And I also want to say one thing. You guys just comment down what's the if you have some queries or something like that, to what you want to say something, you just comment there. And if you have some doubts or something like that, just email me at jelouodsa@gmail.com. So yeah, jelouodsa, just email me there. I will reply to you guys. So that's it. So thank you guys, stay tuned, love and peace.